All right, let's go over this last starter. You're given in A and B a logarithmic function. You're asked to graph it and then to identify the domain and range. Just like with exponential functions, where we identify any shifts that will be in the graph and then kind of deal with that at the end. That's what we're going to do with our logarithmic functions as well. So in part A, what shifts do we have in this graph?
Left 3 down 2.
All right, 3 to the left and 2 down. And so we'll ignore those until the very end and start by just finding some points that are on the log base 3 of x function. And how are we going to obtain these points?
You plug in numbers.
Yeah, we want to rewrite it, really find its inverse. So if we were to rewrite this in exponential form, the exponential form would be 3 to the y equals x. So what is its inverse function?
3 to the x equals y.
Yeah, y equals 3 to the x. And because these are inverses of each other, if I find points on y equals 3 to the x, then all I got to do is switch the x and y coordinates, and then I have points that are on the logarithmic function. It's very easy to find points on an exponential function. We can just plug in our standard set of points. And as I plug those in, I'll get 1/9 for -2, 1/3 for -1, 1 for 0, 3 for 1, and 9 for 2. And then because these two functions are inverses of each other, then I can take all of these points and switch the domain and range, switch the x and y coordinates. So log base 3 of x will have points at 1/9 -2, 1/3 -1, 1 0, 3 1, and 9 2. And now that we've identified points on this logarithmic function, then we apply these shifts. And first off, what kind of asymptote do you have on a logarithmic function?
Vertical.
Vertical. And it starts, for parent functions before the shift, they would be on the y-axis. So if I'm shifting 3 to left, then now we'll be here at x equals -3. A vertical shift would not affect a vertical asymptote, so I don't need to worry about that. And then we'll just take each of these points and shift them. So 1/9 -2, shifted 3 units to the left and 2 units down. 1/3 -1, shifted 3 units to the left and 2 units down. 1 0, 3 to the left, 2 down. 3 1, 3 to the left, 2 down. And 9 2, 3 to the left and 2 down. And so then we'll go along that vertical asymptote and through all these points. And there would be our graph. And what would be the domain of that logarithmic function? -3 to infinity with a parentheses on -3 because we do not include that value. And the range, and then we've already said the vertical asymptotes at x equals -3. We're going to come back to this at the end of class, but when we're talking about logarithmic functions, we want to be able to identify the domain not just from the graph, but also from the equation itself. And you just told me that the domain is -3 to infinity. And what we're going to see is that what comes after this logarithm, this piece right here, cannot be negative and it cannot be 0. It's got to be positive. So how could I indicate that this part of the logarithmic function needs to be positive?
All the x's such that x is greater than -3.
Yeah, so I would start by taking what comes after the logarithm and making it greater than 0. That's going to guarantee what comes after the logarithm is positive. And if you think about your parent function, when you have log of x, then the domain is all the x is greater than 0. So again, what comes after that logarithm has to be positive. If I were to set the x plus 3 greater than 0, then I get x greater than -3, and that proves to be our domain graphically. Okay? So we're going to kind of come back and talk about that towards the end of class and find the domains of logarithmic functions algebraically, but it's good for us to kind of keep in mind that what we're seeing is that what comes after this logarithm has to be positive. All right, for part B, what's the shift that we have? All right, 4 to the right. And we'll ignore that shift. We'll find points on y equals log base 1/2 of x. What would be the inverse of that function?
X equals log 1/2 log.
All right, y equals 1/2 to the x power. We can find points on this function easily. And once we have points identified on the exponential function, and this logarithmic function that's its inverse, we can just switch these points around, and now we know points on the logarithmic function. So we're taking all of these points in the logarithmic function, shifting them 4 units to the right, along with the vertical asymptote. So 4, -2, shifted 4 units to the right. 2, -1, shifted 4 units to the right. 1, 0. 1/2, 1. 1/4, 2. Logarithmic function. And what's its domain? 4 to infinity. Once again, we can see if what comes after the logarithm has to be positive, then if I said x minus 4 greater than 0, I would get that x has to be greater than 4. And that proves to be the domain graphically. The range would be all real numbers, and the vertical asymptote would be x equals 4. Any questions on 1? All right, number 2 gave you some data points and it asked you to find an exponential function that would go through those 2 points. And we did an example like this earlier in the week. What is the equation of an exponential function? What does it look like? Y equals a times b to the x power. And we're going to assume that there's not any kind of horizontal and vertical shift, unless it tells us otherwise. In this case, it doesn't mention anything about any kind of horizontal or vertical shift. So we're just going to assume that there isn't one, which would make the equation of this exponential function y equals a times b to the x power. And what we have to do is we've got to come up with values for a and b. And if I had given you a y-intercept, that would have been really nice. If I had said that the graph passes through the point 0, 4, what would that have told you?
Yes.
That would have told you A, right? That would have told you that the A value is 4, because remember, A represents our initial value or our y-intercept. Now, in this case, I did not do that. So what are we going to have to do with those 2 points?
Plug them in.
Yeah, plug them in, right? If the graph goes through the point -1, 8, that means that when I plug in -1 for x, I get 8 for y. Could even rewrite this as 8 equals a over b with that negative exponent. But is that going to allow us to find either a or b?
No.
But I have another point. Also know that when I plug in 2 for x, I get 1 for y. So I have 2 different equations that relate a and b. So if you think back to when we solved systems of equations before, we could use one of those methods like the method of substitution, which means I would need to solve for one variable and plug it in to the other. So what if I were to take this, a equals a over b, and cross multiply? What would I get? A equals 8b. And knowing that a equals 8b, I could take it and plug it in for a into the other equation. That's how substitution works. Solve one equation for one variable, plug it into the other equation. So I have 1 equals 8b times b squared. So I get 1 equals 8b cubed. B cubed is going to equal 1/8. So when I take the cubic root of both sides, what do I get for b? 1/2. If b is 1/2, then what does a have to be? 4. And so now I know my equation is y equals 4 times 1/2 to the x power. And there would be the exponential function that goes through those 2 points. Questions on number 2?
You can't say y equals 2 to the x, right?
Can't say.
Y equals 2 to the x.
No, you can't, because you have the order of operations would say you'd have to use the exponent before.
You don't have to put in parentheses or anything?
No, you can if you prefer to do that. That'd be fine. Okay, number 3 said to find the domain. We don't know anything about domain of logarithmic functions yet. So we're going to come.
Equal. Wait, I thought we talked.
We talked a little bit about it on number 1, right?
Can't equal. You said it was our 3.
Did we talk about domain?
That was the 3rd one that we had to watch out for.
Oh.
It can't
Yeah,
equal.
I get a little confused because I taught this lesson on Wednesday and then I forget what I've done and what I haven't.
It
Okay?
can't be.
But we talked about the 3 issues with domain, right? One of which is
Square root.
denominators, right? Another one, square roots. But you'll notice we have a square root here, so that's going to factor into part of our domain discussion. We know that what's inside that square root has to be greater than or equal to 0. So we know that x has to be greater than or equal to -2. So that's one part of our domain, is that x has to be greater than or equal to -2. The third issue when it comes to domain is logarithms. Okay? Up until this unit, we had said our only issues with domain are square roots or even roots and denominators. But now we have a third issue, and that is logarithms. And in particular, what comes after the logarithm has to be positive. And what am I going to do with x squared minus 9 is greater than 0? Factor it. It's the difference of 2 perfect squares. And then
You only have to.
test the intervals. Remember, if it's a quadratic inequality, you must test the intervals. So I'm going to put -3 and 3 on my number line. I'm going to use open circles at each of those values. And then I'm going to test a value from each of the 3 intervals on that number line. And it's going to turn out that the intervals that I'm shading are the ones that make that inequality true, that give me, that make x squared minus 9 positive. So this would indicate that our domain would be -3, -3 in union with 3 to infinity. However,
You already have -2.
yeah, I got to put these 2 things together. There's 2 different parts of this domain, and I've got to write a single expression for the domain. So this tells me that x can be less than -3 or greater than 3. This tells me that x has to be greater than or equal to -2. So what would put all of that together?
-2 to -3 union with -3 or 3 to infinity.
No. Why can't I use the part from -2 to 3?
I said -2 to -3 and then union 3. Right.
-3 is on the left side of -2. Here's -2. And so I can't choose, or I can't use any of this because x has to be greater than -2. I can't use anything between -2 and 3 because it's not going to make x squared minus 9 positive. So the only part that's going to satisfy both would be from 3 to infinity. So that's the only part of our domain that we can use. So we have to write one expression that encompasses both of those issues with our domain. All right, and then finally, we have, we're asked to evaluate these expressions, and we talked on Tuesday, I think, how to evaluate logarithms. Is that right? So for log base 8 of a half, we said we could treat that as being equal to x. And what is it going to look like in exponential form? Good. 8 to the x power equals a half. And then from there, we just kind of figure out what x would need to be. So what would you get for x? Negative 1/3. While the negative, make it become a fraction, and then we need to take the cubic root of 8 to get 2, so we would need that exponent to be a third. And then for the next one, log base 2 of 8 plus log base 2 of 1/4. Let's do each of them separately. For log base 2 of 8, rewritten in exponential form would be 2 to the x equals 8. That one's pretty easy. What is x?
3.
And then for log base 2 of a fourth, 2 to the x power is 1/4.
Negative 2.
So, right, the exponent would need to be negative to make the fraction, and then 2 squared would give me 4, so that's negative 2, so that whole expression is equal to 1. Questions on your class start? You had some homework Tuesday night. I have the answers that I can pull up for you. Give you a second to check those. Page 298 in your textbook.
So, on 58, is that the square root still?
Fourth root. Yes, fourth root of 2. Divide through 77. 44 would be 5 to infinity, and 46 would be 1 to infinity. Oh, no, that wouldn't be right on 46. Get it with. No. Gotcha. I think it's 1 to.
Sorry. On 85, I was a little confused because those 2 to the x divided by 3.
Yeah.
What
So
do you do with that?
what I would do is, you have the 4 units up as the shift, and then just take y equals 2 to the x over 3, and you'll notice what I did was I was kind of selective at some of the points that I chose for x. So like instead of doing -2, -1, 0, 1, and 2, I did 3 and 6 and 9 because when I put those in for x, I got, and I don't even know why I would choose, I don't think I would choose 1. I think I would choose like -3 for x or -6 for x. Gets the point.
So you don't take it out, you just leave it there?
Yeah. Just trying to get some points. And then you take all of those points you find and shift them up.
On 97, how do you get from 3 to the 2x plus 1 equals 243 to 2x plus 1?
Because 3 to the 5th power is 243. So I just set 2x plus 1 equal to 5. All right. Any other questions that you want to go over? Homework.
Yeah, 44 and 46.
Okay. We'll go over 46. We had the function was h of x equals log base 3 of x over x minus 1. Is that right? All right. We know that what comes after the logarithm has to be greater than 0. And we haven't really talked about rational inequalities. We talked about how to solve rational equations, but a rational inequality is when you have a fraction as part of an inequality. And we're still going to test the intervals. That hasn't changed from like when we have a quadratic. It's just that in this case, what we're going to do is not only are we going to put the values of x that make the whole thing equal to 0, but we're also going to put any values that cause that expression to be undefined. So what would make this fraction equal 0? 0, because you get a 0 in the numerator. What would cause this fraction to be undefined? 1. So we also make that kind of a dividing, so a number that divides this number line into certain intervals. And then we're going to test the intervals like we would a quadratic. So what's the number less than 0?
-5.
-5. So if I were to plug -5 in, I would get a -5 on top and a -6 on bottom. Does that produce a positive value? Yeah.
Yes.
So that would be included. Then a number is between 0 and 1. So if I did a half, I get a half on top and -1/2 on bottom. Does that produce positive values? No. And then a number greater than 1.
16.
Okay, 16 on top, 15 on bottom. That produces positive values. So the domain here would be from -infinity to 0, and then from 1 to positive infinity. What makes the whole thing equal to 0. And if the numerator is 0, then the whole thing equals 0. Yeah. So for a rational inequality, you always see what makes x equal to 0, but also what makes x undefined. It's really the same thing as quadratic inequalities because you factor it, and then you look to see what would make that factored form equal to 0, and that's what you put on the number line. So whatever makes the fraction equal to 0 or undefined becomes your markers on your number line to test the intervals. Okay? And you do the same thing in 44. All right, what other questions do you have on homework? Yeah.
35 is
All right, 35, we have the natural log of the square root of e. And we're trying to evaluate this, so we're just going to, assume it's be equal to x. And then what is it in exponential form? What's the base of the natural log? E. For natural log, the base is e. If it were just log of the square root of e, then the base would be 10. And if there's no base written, then you assume it to be 10. But for natural log, the base is e. So how would we rewrite this in exponential form? E to the x equals the square root of e. Well, the square root of e could be rewritten as e to the 1/2 power, which means that x is 1/2. And for 36, same thing. Now the natural log of e cubed, so you would write that e to the x equals e cubed, so x would be 3. Any other questions on homework? 58.
But it's gonna be a hard one.
Just find a so that the graph of f of x equals log base a of x contains the point 1/2 -4. So we're just going to replace x and y with these values. So -4 equals log base a of 1/2. Then we're trying to figure out what a would need to be. So I could rewrite this in exponential form, and what would it look like? So that means 1 over a to the 4th has to equal 1/2, which means a to the 4th has to equal 2. And then if I take the 4th root of both sides, a would need to equal the 4th root of 2. Any other questions on homework? All right. Well, our lesson today is on something that you learned back in Algebra with Trig. So it's really not going to be something new to you. It's just going to be a little kind of refresher on using the laws of logarithms. And I've kind of identified, I think, a total of 6 laws of logarithms that you need to be familiar with. Some textbooks have a little bit more, but I think really there's 6 that you need to have some familiarity with. And what we're going to do with these laws of logarithms is 2 different things. In some cases, we're going to take a logarithmic expression that's the log of a really complicated expression, and we're going to expand it out so that we have a logarithm of a bunch of smaller pieces. And then we're going to do just the opposite of that. We're going to take an expression that might have a bunch of logarithms in it and see if there's a way where we can combine them all to a single logarithmic expression. And the way that we're going to do that is by using our laws of logarithms. And this is another one of those lessons where I don't know that I can truly prove to you that you're going to use this very often, but in calculus you will. You will when you start taking what's called logarithmic differentiation. And when you use that, you are going to have to make use of these laws of logarithms a lot. And we're going to use them some when we solve equations on Monday, but by and large, these laws of logarithms are kind of an exercise in taking really complicated expressions and expanding them out, or taking an expression that has a bunch of logarithms in it and consolidating it down to a single logarithmic expression. So here are our first 3 laws or properties of logarithms. And I've kind of created some names for them. I don't know that they're, named this way in your textbook, or any textbook for that matter. But the first one I would say is it's taking the logarithm of 1. Okay? Now these first three, I'm going to kind of go through them pretty quickly because they're really obvious, and especially when you think about how a logarithm is defined, how it can be rewritten as an exponential form. Let's say that we have the log of any base of 1, and I want to know what that is equal to. Okay, so that a could be anything. It could be a 10, where it would just say the log of 1. It could be a 2, or it could be log base 2 of 1. It could be an e, where really we would change it then to be the natural log of 1. But in all those cases, what do you think it would be equal to?
0.
To 0. Why is it equal to 0?
Because anything to the 0 power is 1.
Right. In exponential form, if I were to rewrite this, I would get a to what power is 1. And Nick's right. If we take a value raised to some exponent and we get 1, then it would have to be 0. So log base a of 1 equals 0. If I said the natural log of 1, that's still 0. That's just a special logarithm that has a base of each. So there's our first property. The next property I call the same base and number property. So that would be if I have something like log base a of a. What do you think that's equal to? It's equal to 1. Okay? Because again, in exponential form, this is a to what power equals a. Obviously, the exponent would need to be 1. So if you have the same base and number, or really this is called the argument, same base and argument of a logarithm, then you're left with 1. And for natural log, it would be the natural log of e, because the base of the natural log is e. So since those two e's would be the same, then the natural log of e is just equal to 1. The next property is one we don't really come across a whole lot. It's good to know, although we're not going to really use it a whole lot. It says, if you have a logarithm as your exponent, okay? So now the logarithmic expression is up in the exponent. If the base of the logarithm is the same as the base of the exponent, then they cancel out. So if I have a raised to a power of log base a of x, they're going to cancel out. Well, I guess really the best understanding of that is we've said that exponents and logarithms are inverses of each other, right? So if a logarithm is in the exponent and the bases are the same, the base of the exponent and the base of the logarithm are the same, then ultimately they just cancel each other out. So if we have a raised to a power of log base a of x, then that equals x. Or if we had e raised to the natural log of x, that's going to be just x. So that logarithm being the inverse of the exponent, if the logarithm is in the exponent, then it's just going to cancel everything out and leave you with just x. Good on those three? It's the next three that we're really going to use a lot as we expand out and consolidate logarithmic expressions. And so this first one is called the product rule. Again, you might remember this from algebra trig, but if we have two logarithms with the same base added together, then what happens when we add those two logarithms? Anybody remember? Well, it is kind of like one of our properties of exponents. If logarithms are really exponents, and that's what we said, is that logarithms are just another way of writing exponents, under what scenario do we add two exponents together? We multiply, right? If I had a to the third times a to the fourth, then what would we get? A to the 7th. So the scenario under which we're adding exponents together is really when we're multiplying.
So log A x y.
So it'd be log of A of x times y. I'm not going to write it out, but it still would be true for natural logs, of course. If I have the natural log of x plus the natural log of y, then that would be the natural log of xy. And so we can use this to, like I said, to expand out expressions or consolidate down expressions. Let's say we had log base, as an example, let's say we have log base 2 of 4xy. Well, that's really log base 2 of 4 times x times y. So I could make this log base 2 of 4 and what?
Plus log base 2 of x plus log base 2 of y.
Good.
Can you do like log base 2 of 4 plus log base 2 of x y?
Yeah, but we want to expand it out fully. So we go ahead and separate it out as log base 2 of x plus log base 2 of y. In fact, we could even take this a step further, because what can I do with log base 2 of 4? It's 2, right? We could evaluate that and think of it as 2 to what power is 4. Well, that would be 2. So we really could just make this 2 plus log base 2 of x plus log base 2 of y. And we can go in the opposite direction as well. I could have given you this expression, log base 2 of 4 plus log base 2 of x plus log base 2 of y, and said write it as a single logarithm, in which case you'd combine it all together as log base 2 of 4xy. Well, we have a product rule. We also have a quotient rule. And under what scenario do we subtract exponents? When does that occur? You're dividing, right? So if I were to have a to the 6th divided by a squared, then that would become a to the 4th, right? So for logarithms, since they're exponents, if I have log base a of x minus log base a of y, then what would that be?
Log.
All right, log base a of x divided by y. And you'll notice it's not log base a of x divided by log base a of y. We're writing it as a single logarithm. So it's just a log base a of x divided by y. So if I have the log base 3 of 4x over 9y, then first, based on this quotient rule, I could do log base 3 of 4x minus log base 3 of 9y. So then what is 4x?
Log base 3 of 4 times plus log base 3 of
It's a product, so we can do log base 3 of 4 plus log base 3 of x.
So why would you want to expand these all? Just to solve it easier?
That's the part you're going to have to kind of wait till calculus, because in calculus what you're going to do is, I keep talking about a derivative, you don't really know what that is, but it's going to be a whole lot easier to find the derivative of each of these smaller expressions than it would be this big of them. All right, what do I do with log base 3 of 9y? Is that a product?
Yes.
Yep. So I could write it as log base 3 of 9 plus log base 3 of y. But I got to be really careful, because it comes after a minus sign, and this entire thing was in the denominator, so I'm going to put parentheses around it. And so I don't separate that from that minus sign. And remember, both the 9 and the y are really attached to that subtraction.
Can you simplify that?
Yep. Log base 3 of 9 is really 2. 2 plus log base 3 of y, but all after a minus sign. You could distribute that subtraction sign in and make it minus 2 minus log base 3 of y, then you wouldn't need the parentheses. Everybody good on the quotient rule? All right. Last rule is a power rule. And for the power rule, that's, like if we have a power to a power, like for example, if we have a cubed to the 4th power, that would become
a to the 12.
a to the 12. Right? So if we have something times an exponent, well, for logarithms, the way that would appear would be if we had something like y times log base a of x. Right? Logarithm functions as an exponent, and so if you have an exponent times something, then that's kind of like having a power to a power. So the way that we would write that in terms of this logarithm would be log base a of x to the y power. So it's like having log base a of x as an exponent raised to an exponent. So when you have a power to a power, you multiply them together. That's what we're doing here. We're multiplying the two exponents together. Y is an exponent here, and then the logarithm is an exponent itself. And so when we multiply it, it's a power to a power. And on Wednesday, somebody asked, well, is that y just to the x or to the entire logarithm? It's just to the x. Okay? If I meant it to be to the entire logarithm, it would be log base a of x in parentheses. And in that case, I cannot necessarily move that y to the front. No. It's not. I promise. Okay? So our example would be, let's say we have log, we'll choose a natural log, not that makes really much difference at all, but the natural log of 4x to the 1/2 power. And I want to expand that out.
Natural log.
All right, we've got to be careful. Is that 1/2 to both the 4 and the x, or just the x? All right, so first thing I got to do is separate it as the natural log of 4 plus the natural log of x to the 1/2 power. But now, once I've done that, this property allows me to take this exponent and move it to the front. So I have the natural log of 4 plus 1/2 natural log of x.
Why is it natural log but it's written as ln?
It actually, all right, I used to just make up that it came from the French where they always put the adjective after the noun. So it's like logarithm natural. I just made that, but that's actually true.
Really?
Yeah. It was a French mathematician that came up with the natural log idea, and because he was French, he always put the adjective after.
Every time I write it, I think in my head, lateral log. I'm going to say it all out so I feel stupid.
Wait, how do you just like to use guess French?
Yeah.
You love someone.
Well, there are a lot of mathematicians that were French. Like Descartes. All right, so let's look at some examples.
Should we have homework tonight?
Yes.
Oh my.
I didn't know, maybe he was going to forget.
Like I was going to forget.
Not in the dark one.
It is. You gotta check out that. All right, so the first set of problems that we're going to do is I want to expand the given logarithm to include logarithms with quotient, or power. So that's what your instructions are going to look like for one set of problems on your homework. You're going to have a really complicated logarithmic expression, and what I want you to do is expand it out so that it's the sum or difference of logarithms that include no product, quotient, or power. So we're going to start off with, like I said, a logarithmic expression that's a pretty complicated one. And I want to rewrite this so that I don't have any logarithm that includes a product, a quotient, or a power. Okay? So the first thing we got to identify is what's the main operation in that expression? Division, right? We have this big division bar. And so I could start, and I'm going to show every single step. You may not need to do that, especially as you do more practice, but I'm going to start by showing log base 2 of the numerator minus log base 2 of the denominator. But we're not done because we can continue to shred this apart. That first logarithm, we have 6 times the square root. So there's a product. So I'll make that log base 2 of 6 plus log base 2 of the square root of x minus 1. And then in the second logarithm, I have a product. I have 17 times x cubed times y squared. So I can separate all those by addition. So log base 2 of 17 plus log base 2 of x cubed.
Wait, so it's not minus on all of them?
Well, that's what I was about to show, is because all of these are really linked together, I need to put them in parentheses. Or I could put a minus on all of them. Okay, so now there's no logarithms that have a product or a quotient. It's log 6, log of the square root, log of 17, log of x cubed, log of y squared. But the instruction said no product, no quotient, and no powers. And x cubed and y squared each have an exponent. But what am I allowed to do with those exponents? Move them to the front. So if I wanted to distribute in the negative, which I don't have to, but I can, I would have log base 2 of 17 minus 3 log base 2 of x minus 2 log base 2 of y. And then up here, can't really do anything with log base 2 of 6. What about this log base 2 of the square root of x minus 1?
I feel like you have to do something to it.
Yeah, I could rewrite x minus 1 as having an exponent of a half, and then I could move the 1/2 to the front.
Wait, can you explain why you get 1/2?
So the square root of x minus 1 is
it's like
equivalent
a
to
1/2. Okay, I got you.
x minus 1 to the 1/2 power. And then we can move the 1/2 to the front.
Would you have to do that? Like, would you get marked on it?
We want it as simplified as possible. All right, so now go through each of your logarithms. Do any of them have a product, a quotient, or a power? I mean, 6, that's not a product or a quotient or a power. X minus 1 is a difference, so there's nothing I can do with that. 17, x, y, none of those are a product or a quotient or a power. So we've taken a really complicated logarithmic expression and expanded it out to a bunch of smaller pieces. All right, you try these two.
I like these. Have you looked at box? This box.
I'll wait any day.
Really? Alright, when we box it.
Literally no question.
When we box it. I said when.
Said he wants the box.
All right, you try these two. All right, let's see how we would expand out this first one. Main operation is the division. So I'll do log base 4 of the numerator. And how can I rewrite the 4th root of y cubed as having an exponent?
3/4.
Y to the 3/4. Okay? And that's helpful because we know at some point I'm going to move that 3/4 to the front as an exponent. Then I'll say minus log base 4 of 7 times x plus 2 squared. And then I have some products. I have 16 times x cubed times y to the 3/4. So that would be log base 4 of 16 plus log base 4 of x cubed plus log base 4 of y to the 3/4. Is it important for us to put that base 4 each time? Yeah, because if I don't, then I've completely changed the problem. Now I've got log base 10, because if there's no base there, then I have to assume it to be 10. So it's really important that you put the correct base of each logarithm. All right, then minus, and I'm about to separate this out. Can I move the 2 to the front? Not yet, right? I got to separate out the 7 first. So it's just x plus 2 squared behind the logarithm. All right, log base 4 of 16. Anything we can do with that? It's 2, right? 4 to what power is 16? That would be 2. Here, this exponent can move to the front. Here, the exponent can move to the front. I could distribute in the negative. Anything I can do with log base 4 of 7?
No.
Now, it doesn't come out evenly, so there's no reason for us to attempt to evaluate that. So we'll just leave it as log base 4 of 7. And then for the last one, we would move the 2 to the front. Oops, forgot I was distributing in that negative. So we move the 2 to the front, log base 4 of x plus 2. I think we have written it so that no logarithm has a product, a quotient, or a power. You don't have to. All right, and then for this one, I'm going to run through this one fairly quickly. Same thing. It's quotient again, so I'm going to do the natural log of the numerator minus the natural log of the denominator. I can make this the natural log of 8 plus the natural log of x plus 1 to the 1/3 power. And then minus, I can have the natural log of 3 plus the natural log of y plus the natural log of x squared minus 9. And anything we can do with the natural log of 8? Plus 1/3 natural log of x plus 1 minus something we can do with the natural log of 3 minus the natural log of y minus, there is something we can do here. X squared minus 9 is the difference of two perfect squares. And now what is x plus 3 times x minus 3? A product. And that can be separated out. Okay?
Square minus.
So we have to separate that out. It's not fully simplified if you don't factor it and then separate. Okay? So we have the natural log of 8 plus 1/3 natural log of x plus 1 minus the natural log of 3 minus the natural log of y minus the natural log of x minus 3 minus the natural log of x plus 3. Okay? Really, it was a plus, but then when I distributed that minus sign, both of them would be negative. All right. And one last problem, and that is just going in the opposite direction. What we've done is we've taken complicated logarithmic expressions and expanded them out so that they're the sum or difference of a bunch of smaller ones. But we can do just the opposite. We can take one that's already been expanded out and consolidate it down as a single logarithm. So the instructions would change now and say write as a single logarithm. Let's say we have log base 2 of, let's do 4 log base 2 of x minus 1 minus 1/3 log base 2 of 2x plus 3 squared plus 4 log base 2 of y. So we have a expression that contains multiple logarithms, and we're going to try and write this as a single logarithm. The first thing you're going to want to check is look at the base of each of those logarithms. What has to be true of all those bases?
They have to be the same.
Be the same. If they're not the same, I can't combine them. Okay, so if I put like log base 2 here and log base 7 here and log base 5 there, I really couldn't do anything at all. Okay? They have to be the same base for me to combine them.
So we do that with a test, so we don't do anything.
Not on purpose. All right, now remember what we're doing is we're going in the opposite direction. So, in the previous example, one of the last things that I did was take any exponents like this 1/3 and move them to the front. So if I'm going in the opposite direction, one of the very first things I'm going to do is take any numbers that are in the front and bring them back up as exponents. So this log base 2 would now be x minus 1 to the 4th power. This next logarithmic expression would be log base 2 of 2x plus 3 to what power?
The 6. Oh wait, no. It's the cubic root, but it's
All right, so it would be 2/3, or the cubic root of 2x plus 3 squared. And then the last one would be log base 2 of y to the 4th. And then order of operations is taking over, and in order of operations we do addition and subtraction at the same time from left to right. So I'll start actually with this subtraction sign. And so I'm combining two logarithms that have the same base. So I'm going to write it as a single logarithm and do what?
put them out like dividing.
Divide. So it would be x minus 1 to the 4th power on top, and it would be the cubic root of 2x plus 3 squared in the denominator. And if you left it as 2x plus 3 to the 2/3 power, that's fine too.
I had a question though. With it being fully expanded, whenever you give us the equation, how can I have an exponent over 2x plus 3?
It wasn't fully expanded. It was still expanded somewhat.
Is it going to be fully expanded with test?
I mean, it might be.
If we
You're still trying to get it all together as a single logarithm.
if we put log 2 fully combine it with the x minus 1, so we have log 2 on the top and the bottom.
That's wrong.
That's
It's
wrong.
a single logarithm. Okay, so it's got to be log base 2 in the front of that entire expression. That's a good question. I'm glad you asked that because that's something a lot of students mess up on. It's a single logarithm in the front. All right, now we have two logarithms that we're multiplying. What happens when I take a fraction times an expression? Where's that y to the fourth going to land?
The top.
In the numerator, right? So we're going to have log base 2 of x minus 1 to the fourth power, y to the fourth, over the cubic root of 2x plus 3 squared. So there's our single logarithm where we've consolidated all of those expressions into one. And that skill of being able to take multiple logarithms and combine them together as a single logarithm will be helpful on Monday when we solve logarithmic equations. Because one of the first things we're going to want to do is make it so that we have only one logarithmic expression. Like in the last unit when we were solving trig equations, we wanted only one trig function. So we'll make use of that some as we solve equations on Monday. But here's your homework. Be prepared to go over this on Monday.
If we were out the last day,
Yeah, I taught this lesson on Wednesday. And then I wasn't here yesterday.
You're calling out names or good?
how do you pronounce Vidal? Is it not Vidal? I thought it sounded weird whenever it's like that. Vidal? I work for his cousin. That's why they all pretty much get it. Tommy, it's so